Okay, so we are going to see lecture 17, and this is a lecture on, well, we are going to see how far we go. First, let's start with combinations and permutations. Then binomial, Poisson, Gaussian distributions. And then general properties of distributions. Okay, so so if I give you n objects and different objects, what are the total number of arrangements? Number of arrangements, or we can also call permutations of n objects. N objects. That's n factorial. Well, how do we show that? So let's say I have n objects. Object number 1, object number 2, object number 3. So for the first slot, I have n options. Then to fill up the second slot, I have n minus 1 options. Third slot, I have n minus 2 options, so on and so forth. 2 options, 1 option. So all these ways are n factorial ways. Now, let's say I have n objects, but I need to see the permutations of m of them at one time. M of them at one time. Which can be called as the number of ordered subsets containing m objects out of n. That, by the same reasoning, the first slot I'll have n options, the second slot I'll have n minus 1 options, so on and so forth till n minus m plus 1 options I'll have. So this way I'll have m objects out of n of total number of n objects, and the total number of ordered subsets, or the number of permutations picking m of them at one particular time, is n minus 1 factorial. This is this thing. Okay, so we can ask, so this was about permutations. What about combinations? So combinations is we ask for the number of subsets, let's say number of subsets containing m objects out of n without regard to the order in which they appear. So that's called as the number of combinations of n objects taken m at a time. Okie dokie. So how would you calculate that? Well, we would divide the above result, n factorial over n minus m factorial. Divide this by m factorial because that's going to take care of the different arrangements of the same group of m objects chosen. So that turns out to be what is known as n choose m, which is this guy, also known as the binomial coefficient. So we can ask some other interesting questions. For example, question: how many distinguishable arrangements are there of n objects if n1 are identical or of the same type, n2 are identical of a different type, are identical of a different type, so on and so forth. So the total number of permutations is n factorial, but each distinguishable permutation appears n1 times, n1 factorial, n2 factorial times, so on and so forth, nr factorial or something like that times. So this is going to be the number of distinguishable permutations when n1 are of one type, n2 are of second type, so on and so forth. So what is an example of, let's do a slightly trickier question now. So the question is the following: how many combinations of n objects how many combinations of objects taken m at a time if we allow repetitions, if we allow repetitions. So think about it. So let's say I have three objects. Again, I can number them as object 1, object 2, object 3, and I take two at a time. So I have 1 1, 1 2, 1 3. Remember, I am allowing the repetitions 2 2, 2 3, 3 3. So I have, the number is 6. 6 of them are there. How do we derive a general formula for derive a general formula for the above? So one way to do this is the following, is to recast this problem in some other way. So this is like, let's say you have it all boils down to, let's say you have these partitions and have these x's. So the first would correspond as this guy. This is the first thing. I have xx of one type and these partitions, nothing here, nothing here. 1 2 would correspond to x in the one box. So this can be regarded as box 1, box 2, or box 3. And the idea is to place these x's in the boxes such that this corresponds to this particular mapping. So this would be xx and nothing in this box. What will be 1 3? This is going to be x. This one is blank. This partition is x. Then what would be 2 2? 2 2 would be just this guy. And we'll do just one more. So for example, certainly 3 3 is going to be this guy, and 2 3 is going to be this guy. So what does it boil down to? It is placing these number of x's and these number of sticks around each other, and what way you can do that. So how much does it correspond to? So you have uh, m x's, and you need essentially n minus 1 number of sticks or vertical lines arranged in a permutation, and that is going to give you the total n minus m factorial divided by n minus 1 factorial. Remember, the number of total permutations of m plus n minus 1 objects when n minus 1 are of one type and m are of one type, m factorial, this thing. So this is a general formula for the number of permutations of n objects taken m at a time when you allow repetitions. So this way you can construct essentially with some thinking and some counting arguments, you can consider doing very rich problems in permutations and combinations. Okay, so now let's go to the binomial, Poisson, and Gaussian distributions. So this is done. So let's return to probability theory and ask for the probability of exactly H, exactly M heads in a coin toss if a fair coin is flipped n times. The result of n successive coin flips can be represented by a sequence. So it can be like H, H, T, H, T, T, H, so on and so forth. So probability of one of these sequences is just 1 over 2 to the power of n, because well, probability of getting a half is 1 by 2, probability of getting another heads is 1 by 2, probability of getting tails is 1 by 2, and since these are all independent events, that's the probability, the multiplication of all of them. And the number of such, I mean, what is the number of successful events? Well, that's just n factorial over m factorial n minus m factorial. Essentially, it is n choose m. Out of n coin tosses, I'm choosing m heads. That's going to be it. So the probability we are after is probability of m heads or m successes is just n choose m times 1 over 2 to the power of n. So we can generalize this slightly. Essentially, when I have m successes and n minus m failures, and the probability of success is p, and the probability of failure is 1 minus p. So the above can be done as n choose m, p to the power of m minus p to the power of n minus m. Okay, so this probability distribution is known as binomial distribution. Binomial distribution. So there are two important limits of this binomial distribution. So this is clearly, I can write it down explicitly as so there are two important limits of the binomial distribution, which is to say and both these limits are for large n, a very large number of trials. Large n, in the first place, suppose that n and piece of n, which is the probability of success times n, are fairly large, are large. So what do you expect when you have, let's say, many coin tosses and like n is large? What do you expect the probability piece of m, the probability of m successes. How is the distribution of probability of piece of m going to look like? Intuitively, you can think about it that it should be maximized at somewhere n times p, which is the probability of success at one trial and times the n. So this is the mean near this sort of a thing. So this is the probability that probability distribution uh, of m would be some. So this is mx's, and I'm calculating the probability distribution per se. Intuitively, you would sort of guess that if I have n trials of p success, then this product would be roughly where this probability distribution function is going to peak, and you can intuitively check that notion. So, for example, you have a fair coin and you throw it 100 times. Well, it should peak around. We don't know why it should intuitively peak around. The most likely answer is that for a fair coin, it should be 50 heads. So that would be just n times p. So we capture this intuition using the Stirling's approximation. So this is a very useful approximation, which I think can be recast into many avatars. But the best way to write down this is the following, which is to say, so log n factorial. It's the approximation of n factorial, essentially n log n minus n plus some term of the order of log n. So that's how you approximate this thing. And more precisely, you can actually express this as n factorial. I shouldn't call it equal, I should just call it something. Well, this is equal is fine, but this approximation is something like 2n over e to the power of n. So a lot of times you just use log n factorial to be n log n minus n. You neglect this guy, but this is the more precise formula to approximate n factorial by n over e to the power of n times some factor square root of 2 pi n. So we will be using this expression, and this is an exercise for you. So work it out, this thing, in this expression, and that is going to give, so I'll write it out again. So probability of piece of m was given by this guy, n factorial over m factorial n minus m factorial piece of m 1 minus p of n minus m. So that was my thing over here, and in this I use the Stirling's approximation, which is to say this guy. I can use the same thing for m factorial also. When n is large, I roughly know that m is also m is peaked around, m is approximately peaked around piece of n. So I can replace even m factorial by some sort of a Stirling's approximation, and I'm going to get piece of m equals to square root of 2 pi n. Uh, yeah, that's coming from over here somewhere. And that is going to boil down to m over n minus m minus half n minus m divided by n minus n plus m minus half. So this is just algebra. You need to figure it out, and I would urge you to figure it out yourself. All we are doing is in the above formula plugging in the Stirling's approximation, and then we are all set. So this can be expressed as so e to the power of log y. Let's say this is x as an aside. I take log of both sides. I have log y equals to log x, hence x equals to y. So e to the power of log of y is nothing but y. That's what I'm going to use here. I'm going to express this guy as 1 over square root of 2 pi n exponential. I'm going to express this now. I'm going to take the log of these guys. So I'm going to put e to the power of log to the power of this guy, which is nothing but the same guy again. So exponent the log of the this jazz, which is going to be minus m plus half. So don't crack your head on it. It is just algebra. If you see the notes and do it yourself, you will arrive at the same answer. I don't know how better to explain algebra. We'll try to go as much step by step as possible. Plus m log p. So I'm using log and natural log. For me, log is log. A bit clumsy, but we'll just continue. N minus m log 1 minus p. So I have taken the exponent and taken the logarithm of this guy, which is nothing but this guy itself. And now what I'm going to do is that I'm going to just replace, I know that m, intuitively I know that m is peaked around np, so I'm going to just write np plus some epsilon over here, and where this epsilon, let me consider to be much smaller than np. And if I retain just the dominant terms, I'm going to get piece of m as 1 over 2 pi n 1 over p 1 minus p exponent of 1 over this psi square to np 1 minus p. So this is terrific. My binomial distribution in the limit of a very large number of trials, and when I had NP to be quite large, uh, I got it to resemble a Gaussian. So there is this way of treating these independent coin tosses or something like that in the limit of large number of tosses, where each trial there is a finite probability. So I should say this limit is large number of trials, large number, no? And at each trial there is a finite probability of success. In that limit, my probability distribution associated with the success resembles a Gaussian. Now, I can write it in a much more convenient form. I'll just write it down as piece of m equals to 1 over 2 pi sigma exponent of minus half. So I just define sigma, which is the variance, as nothing but this guy. So it's a measure of the width of the distribution. Distribution. So the second limit of the binomial expansion, I'll just write it down again, the binomial distribution for m. P to the power of m minus p n minus m. Second limit of interest is when n is very large and the probability of success in each of those trials tends to 0, such that this number, a very large number times something, limit goes to infinity, limit goes to 1, is inside some finite number, a. So under these circumstances, my n factorial over n minus m factorial would go to n to the power of m, and my 1 minus p to the power of n minus m would go to 1 minus p a to the power a divided by p, and that is going to be nothing but e to the power of minus a. Remember the limit, how you take the limit of this thing, 1 plus x to the power of 1 plus 1 by x to the power of x, as well, x goes to infinity, that goes to e. So that's what we used over here. So and of course in this expression and formula, this is valid when m is much smaller than n. That's why we were able to use this step and just use this step. So essentially combining these results, 1 minus p replacing it by e to the power minus a, and this guy as n to the power of m, what do we get? We get the distribution function starts to look like m e to the power of minus a divided by m factorial. So I use this guy to evaluate this guy, and I use this expression for this guy. Okay, so what do we have? So this is known as the Poissonian distribution. Poissonian distribution, which tells me the probability of the success, m successes, is given by this guy when a is when a is equals to np, on an average how much success I am going to get. So when is this limit valid? As we said that this is valid when n is very large and the probability of success at each trial is going to 0. In the physical context, we may think of, so in a realistic scenario, when is this Poissonian limit valid? Well, let's say when probability that m calls are made to a switchboard, to a switchboard, let's say in 1 second. In 1 second, we roughly know on an average how many calls are made in a longer time. We need to calculate how many calls are being made in a very short time. So that probability would be given by a Poissonian distribution. The other example might be the distribution of cosmic ray counts, so on and so forth. Uh, and so that's the idea. I mean, the historically Poissonian distribution was modeled by the number of horse kicks uh, in some uh, stable of horses or something like that. So the probability of each kick was very small, but we were considering a large number of sample, and these were all independent experiments. And what is the probability of m kicks of a horse? And this was given by some expression like that. When we knew some value a, average number of kicks in some time, what would be the probability of m such kicks? So that's in general the why am I calling uh, just a second. If you calculate the expected value of m successes, that's going to come out to be a. That's why I'm calling a to be the mean. So if I know the average value of a quantity, how does that quantity out of an independent event occurs? That would be given by a Poissonian distribution. So, well, there can be number of patients arriving in an emergency room in a particular time interval. Each patient arrives independently. I know something about the average number of patients. I'll model it through a Poissonian. Number of photons, laser photons hitting a detector, number of meteoroids greater than some diameter striking the earth. So these are all the examples of a Poissonian distribution. And remember, we started with the binomial distribution and we took this limit. The number of trials are going very large, where the probability of success in each of the trials is very small. And then in that limit, we were able to derive the distribution of m successes to be something known as the Poissonian distribution. Okay, so that was about uh, general properties of Poissonian binomial and Gaussian distributions. In the next class, we are going to study the general properties of distributions. Thank you.